Morning. I'm going to finish today considering the parametrics method for constructing fundamental solutions to the Kolmogorov backward equation. And I would like to recall that we have coefficients A, J, S, X, and B, I, J of S, X for S, X from 0 to T, or D. Positive T is fixed. I and J from 1 to D. And we suppose that the matrix BSX is such that this form is greater than C1 absolute norm theta squared and C2 for any theta from RD, where C1 is a positive constant and it is less than or equal to C2. And the functions Bij of Sx were supposed to be Hölder continuous in both arguments S and X, and Ij of Sx were supposed to be continuous bounded and Hölder continuous in the space arguments. Okay, and we constructed some function g0 of s x t y defined by the following expression: 2 pi t minus s to the power d determinant b t y to the power minus 1/2 x minus b t y minus 1 y minus x y minus x t minus s is defined for s less than t and x from RD and y from RD. And this function we saw that this function was such that g0 s x t y can be estimated by some constant t minus s to the power minus d over 2 x minus mu y minus x square over t minus s, where k and mu are some positive constants. Moreover, if let us denote by L the parabolic operator associated with our coefficients, that is LU is equal to U prime over S Sx plus A Sx U prime over X Sx plus 1/2 trace B Sx U second prime Sx. Okay, and we saw that if we apply the operator to this function as a function of the first two arguments for fixed t and y, then the absolute value of this expression can be estimated by some constant. I will denote it again by the same symbol, k t minus s to the power minus d plus 2 over 2 plus alpha over 2. Alpha is a constant from the following inequality. K t minus s to the power alpha over 2 plus x minus y to the power alpha. I have already mentioned that this function satisfies the Hilbert condition with some constant k. K is a symbol of a constant that is not it is important for us that there exists some constant such that alpha is the same in this inequality, and exponent minus mu y minus x square over t minus s. And this allows us to for the fundamental solution to that equation in the following form: g s x t y is equal to g0 s x t y plus integral the tau integral over d g0 s x tau z q tau z ty dz. Where q tau z ty is an unknown function, and we are looking for this function, and the reason how to find it out are as follows. We know that a fundamental solution must be a solution to the equation LG equals 0 as a function of the s and x for fixed ty. It must satisfy our equation. Okay, so if I apply to this equality that operator L, I should receive here 0, here L, let us denote this function by R S X T Y. Okay, so R S X T Y plus there is the derivative of u with respect to s. We have s here twice in the two places, here and here. Derivative with respect to this gives us minus integral this integral at the point tau being equal to s. And we saw that we have proved the following property of the function g0. g0 s x tau z f tau z dz converges to f of s x for any continuous bounded function if as tau goes to s. So we can write down here minus q s x t y. Okay, this is the limit of this function at the point sx. Okay, and plus the integral term, the tau integral over rd r s x tau z q tau z ty dz. And now we have the following integral equation. Q is equal to R Sx dy, and this equation is of the Volterra kind, and it is solved by the method of consecutive approximations. Q0, we put Q0 Sx ty being equal to R Sx dy, and Qk Qk Sx ty is equal to the integral over the interval from S to T, the tau integral R S X tau Z Q K minus 1 tau Z Q Y dz. And if we obtain some appropriate estimations for Qk, then the solution of this integral equation will be represented as the sum of all Q, K, S, X, T, Y. Q, S, X, T, Y equals. Okay, and to obtain those estimations, we need the following auxiliary result. Suppose that we have two functions, h, I, s, x, t, y, for I equals 1, 2, such that absolute value of h, I is not greater than some constant. I would like to denote it by k, or maybe this is not our situation, this is a proposition. So ci t minus s to the power minus beta I, and exponent minus mu y minus x squared over t minus s. Okay, and if I form a new function that is in some sense the convolution of these two functions, h1 of s x tau z, h2 of tau z ty dz. Denote this function by h s x t y. Okay, and then we have the following estimation for this function h s x t y is of the same type as these functions, so some constant t minus s to the power minus beta exp minus mu y minus x squared over t minus s, where c equals the product of C1, C2, square root of pi over mu to the power g, Euler's beta function, d plus 2 over 2 minus beta 1, d plus 2 over 2 minus beta 2, and beta is beta 1 plus beta 2 minus d plus 2 over 2. You see, beta is less than any of these beta 1 and beta 2, because it can be written as beta 1 minus d minus, oh, I forgot to say here that beta I must be less than d plus 2 over 2. I'm sorry, I forgot to. Beta I is strictly less than d plus 2 over 2. So d plus 2 over 2 minus beta 2 is a positive number, okay? So beta is less than beta 1, and the same beta is less than beta 2. So this estimation is better than any estimation for HE for I equals 1 and 2. Okay, but here must be written minus beta, and it was my mistake. I am sorry. I wrote last lesson here beta, but here must be written that constant c. Here is written c t minus s to the power minus beta. That is d plus 2 over 2 minus beta 1 minus beta 2. Okay, and exponent Professor Portenko was that one who drew my attention to this mistake. I'm sorry. And I'm thankful to Professor Portenko. Okay, and now applying this auxiliary proposition, we can receive the following estimations on the QK. For Q0 we have already had estimation, yes. And now for QK, by induction on K, we easily arrive at the following estimation. K to the power K capital to the power K plus 1 pi over mu pi over mu to the power K G over 2 gamma of alpha over 2 to the power K plus 1. Okay. T minus S to the power K plus 1 alpha over 2 minus G plus 2 over 2 over gamma Euler's function gamma K plus 1 alpha over 2 and exponent mu y minus x squared over t minus s. Okay, and now we see that this series is indeed convergent. Okay, and that convergence is uniform in all arguments. Maybe I explain. Let us write down that series in the following form. Let us write down t minus s t minus s to the power minus d plus 2 minus d plus 2 over 2 minus plus alpha over 2. Okay, let us that factor right before this sum. Okay, so under the sign of this sum we will have t minus s to the power k alpha over 2. Yes? And it is less than t to the power k. So the sum of all the qk can be written as some new constant n. Okay, this is the sum of all these terms when t minus s to the power minus d plus 2 plus alpha over 2 written separately. Okay, and the exponent mu y minus x square over t minus s. You see, this estimation is quite similar to this one. This is our kernel R S X T Y. And now we can write down the following estimation on the fundamental solution. On this function gsxty, that is, we have already had some function q, okay, and we have some estimates for it. So we can we see that function can be written as the sum of two functions, g0 and g1 as x, p, y. Okay, we have for g0 we have it is non-negative, this function, and we have this estimation for the function g0. Okay, and now let us estimate g1, absolute value of g1 as x ty. So we have here g0, it satisfies this inequality, and q. So we have a situation described in our auxiliary proposition. Okay? Beta 1 is d over 2. Beta 2 is d plus 2 over 2 minus alpha over 2. Okay, so G1 beta is equal the sum of these G plus 1 minus alpha over 2 minus d plus 2 over 2. Okay, d over 2 minus alpha over 2. Okay, and we should write it with the t minus s to the power minus beta. Okay, so I have some constant. Maybe let us write down some other letter. Some constant m, t minus s to the power minus d over 2 plus alpha over 2, and exponent minus mu y minus x squared over t minus s. And you see, this estimation is better than this one. So the main singularity of this function is concentrated in this function, g0. And we saw that integral over Rd g0 s x dy phi of y dy converges as t minus s goes to 0, converges to phi of x for any bounded continuous function phi. Okay? And if I consider the same integral for the function g1, so this estimation shows that absolute value of this integral is less than n norm phi, and that integral gives us t minus s to the power plus d over 2. Okay, so t minus s to the power alpha over 2, and that integral over d e to the power mu dz. And we see that this goes to 0 as t minus s goes to 0. So this function, so we have already seen that this function as a function of the first two arguments must satisfy the equation L gsx dy is equal to 0 as a function. So it is not difficult to see that it is continuous in all its arguments. Okay, and it satisfies phi of 2y dy goes to phi of x for any continuous bounded function as t minus s goes to 0. So this is a fundamental solution by the definition. Okay, now let us continue our lesson. So I have just explained the idea of the parametrics method for constructing a fundamental solution. There is a great deal of details and you can find them in the books. For example, by Friedman. It is called partial differential equations of parabolic type. It was published, as far as I remember, in 1964 maybe. And there is another book by Ladizhinskaya, Solonnikov and Raitseva, where you can find all the details how to construct the following properties are exposed in those books. They proved that the following estimations are fulfilled. D L S D M X G S X T Y absolute value. DSL is the derivative of this function as a function of s, and that derivative is of the order L. Okay, and this is the symbol of any particular derivative with respect to x of this function as the function of x of the order m, and L and m are connected with the following inequality. 2L plus m is less than or equal to 2. And this estimate is as follows. K t minus s to the power minus d plus 2L plus m Okay, so if L equals if L equals 0, then M may be equal to 0, 1, and 2. Okay, and if L equals 1, then M equals 0. So these estimations are the main aim for specialists in this topic. Okay. So now we have some notion about how to construct a fundamental solution to our equation, and now we should look forward to a possibility to answer the following questions. The first one, is that fundamental solution non-negative or no, or not? Okay, this is a very important question for us as probabilists, as specialists in probability theory. Is that solution non-negative or not? The following question: does it satisfy the Kolmogorov-Chapman equation or not? These questions are very important for us. So we start from we start answering the first question. I would like to show that this solution takes only non-negative values, and the main idea is the following one: if I consider the integral gsx t y phi of y dy, so this function is a function of sx is a solution to, if this function is usx, okay, then it is a solution to the following equation: LUSX equals 0, and it satisfies, if phi is bounded and continuous, it satisfies the initial, in the sense of final condition. This is phi of x. This equation is fulfilled for all s x from 0 to t, and this condition is valid for all x from Rb. T is fixed here. So, if I prove that the solution to this problem is non-negative, if phi is non-negative, it will be that we need it, okay? Because if I know that this integral is non-negative, if phi is non-negative, then this function is continuous, then, and it is valid for any bounded continuous function with non-negative values. So this function must be take on only non-negative values. Okay? So we now start to consider such a problem. What one can say about the solution to this problem if we know that on the right hand side we have here in this condition a continuous bounded function with non-negative values, and the topic connected with this question is called the maximum principle. Maximum principle. And we can we start considering the following region, denoted by a fixed t, denoted by dt, not d, maybe okay, dt. Is the set of all tx such that t is from the interval t and x is from the Euclidean space Rd. Okay, and now denote by D the following region Sx from dt such that S is from 0 t and norm x is less than r. R is a positive number. So this is a cylinder. Okay? And S is its lateral surface. Okay, so we have cylinder and its lateral surface, and S0 is such that S equals 0 and X is less than R. And ST equals to that Sx from dt such that S equals t and X is less than R. So this is the front lid. And this is the rear lid. Okay? And suppose that the region S0 plus D is an open cylinder, okay? And suppose that in the region S0 and D, the coefficients A, J of Sx, B, I, J of Sx, and C of Sx are given for J and I from 1 to B. And suppose that these coefficients are continuous functions. B Sx is Bij are such that the matrix Bsx is non-negative definite. And all Sx in that region. Okay, and we consider the following, and the following assumption: Csx is non-negative, non-positive. Excuse me, I'm sorry. and we consider the following operator: L U S X equals C S X U S X plus the sum over OJ I J S X U prime X J S X, and plus we will not write down here 1/2. In these topic, 1/2 does not matter. J I from 1 to D, J I J S X U second prime X I X J S X. So the following assertion is true. Let us call it proposition. Proposition 1. If we have a continuous function u s x on the closure of this cylinder, a continuous function such that it is differentiable with respect to S in this region and twice continuously differentiable in this region with respect to X, and such that if I apply that operator to the function, to this function USX, I have this inequality. LUSX is non-positive for all SX from this region, 0 plus B S0, the rear lid and the interior of our cylinder. Okay? Then maybe okay. Then maybe it would be better to say if minimum USX over OSX from D closure, from the closed cylinder is negative, then this minimum is the same as the minimum of the same function, usx, taken over all sx from the lateral surface. From S lateral surface and ST. This is our initial assumption. If this function takes, if the minimum over the closed cylinder is strictly negative, then that minimum, there is a point on this surface such that that minimum coincides with the minimum of this function over these two surfaces. Okay? We will use this lemma in the following way. If I have some function that satisfies this inequality, and I am capable or able to see that its minimum over lateral and front lid is positive, so the function must be positive in all this cylinder. Okay? As you remember, it was very important to us know that if on the final point our solution is positive, then it is positive at any point before that final instant of time. Okay? So let us prove this proposition. As a rule, such theorems are proved the following way. Suppose that it is not true. Denote this minimum by M and this minimum by M capital. So suppose that M is strictly less than M. Then there exists a positive number mu such that mu plus M plus mu is less than minimal of the numbers 0 and M. Okay? If this minimum is strictly negative, then we can find out such a number, such a positive number mu, that M plus mu is less than 0, and m, if m is negative, m plus mu is strictly less than m, and if m is positive, no, m plus mu is less than 0. And consider the following auxiliary function. Vsx equals usx plus 1 over t mu over t minus s. Okay? It is defined, this function, on the closed cylinder. Okay? And what we can say about this function? The first property of this function, L V S x is equal L U S x now minus the derivative of this expression with respect to s minus mu over t and plus c s x mu over t minus s. Okay, so I know that this is non-negative, this is strictly negative, okay, and this function is non-negative, and this number is positive, non-negative. Okay, so we have that this function satisfies, as a consequence of this, we have LVSX is strictly negative at any point Sx from this region, S0 and D.
I can't understand. Do you have derivative with respect to S in operator L?
Yes. Oh, I am sorry. You are right. Again, you are right. U prime over S, Sx should be written here. Okay. U prime over S, U prime over U second prime. Okay. So we have here this derivative with respect to S. This is the result. Okay, and this term is written here. So we have this property, the first. The second, let us consider this function. Let us consider minimum of the function Vsx over all Sx from the closed cylinder. You see, the minimum of this term is m. okay, and here something positive is added. So and that positive is not greater than mu. If s equals 0, we have here mu. So I can estimate that this minimum, that it is not less than m plus m. m plus mu. M plus mu, okay? And this m plus mu is strictly less than that. And the third property, let us consider the minimum Vsx over Sx from the lateral surface and the front lid. Okay, I know that this minimum is m. Okay, and something positive are added to this minimum. So this minimum is not less than m. So you see, the minimum over the closed cylinder is negative, and it is less than m, and minimum over the lateral surface and the front lid is greater than m. So there exists a point S0, x0 from D plus S0 such that Vs0 x0 is equal to that minimum. Minimum over Sx from D bar Vsx. And now our aim is to observe that L applied to V is such a function that must be non-negative at the point S0, x0. And it will contradict to this property of our function. Okay? But now this is a very simple observation, because you see, if S0 belongs to, so S0 must be either 0 or some number less than t. Then U prime S at the point S0, x0 must be either 0 or some non-negative number. Okay? Because if it is minimum s at 0. If s0 coincides with 0, then minimum here, and this derivative maybe either positive or 0. Okay, and if this is an inner point, so this derivative is 0. These derivatives at the point x0 equals 0, because that is the point of minimum, and this at the point where this function takes its minimum, attends its minimum, this term is, and we have that this function is non-positive, and v at the point s0, x0 is negative, okay? So this negative and non-negative and non-positive, we have that this is also less than or equal to 0. So L V S 0 x 0 must be non-negative. And this is contradiction to this property, okay? And this contradiction arose because we suppose that M is strictly less than M capital. So the proposition 1 has been proved. Okay? So my time is over. See you next Tuesday.